So this adventure in algebra, we're going to continue studying cosets, and we're going to look at attempts to look at the converse to Lagrange's theorem. So we'll state what that means in a moment. The point is to try to figure out when you have a subgroup of G of a given order. So one of the things you get from Lagrange's theorem is that if H is a subgroup of a group G, then the size of H divides the size of G. You can ask the converse, which is that if you have a group G of order n, and you have a number D that divides n, does there exist a subgroup H and G with D elements? The answer will turn out in general to be no, and that's the goal of this video, which is partly optional. But before I go on, I will point out that there actually is a version that we don't cover in this course that sort of works, which says if D is prime power, then yes, there does in fact exist a subgroup of G with size given by a prime power. It was called his first CELO theorem because there's actually 3 CELO theorems. This is actually a corollary of the first CELO theorem. The first CELO theorem actually talks about the largest prime power that divides the order of the group. And then the other ones actually talk about the structure of such groups. It's a very deep theorem, and it's actually very complicated. But we're going to focus more on this question and disproving it. Here comes an incredibly mean question. So suppose your group has order n, and suppose D is a divisor of n. Is it necessarily the case that G has a subgroup of order D? So we've already shown that if H is a subgroup of G, then the order of H has to divide the order of G. But what about the opposite? It turns out the answer is no, in general, that there are counterexamples, but finding the counterexamples is really hard. In fact, the smallest counterexample involves n being 12. Because it turns out if D is a prime power, then the answer is yes. So 6 is the smallest non-prime power, and the smallest number that 6 can divide besides itself is 12. So this is the smallest case you can find. So G is the alternating group on 4 vertices, 4 elements. It has size 12. 6 divides 12. You can actually prove that A4 has no subgroup of order 6. And how do you prove this? Well, observation 1, the elements of order 2 less than or equal to 2 form a subgroup. Of order 4. So in other words, if you want a subgroup of order 6, then H is going to have a 3 cycle, because the elements of order 2 aren't going to be enough. Alright, so this is an attempt at a proof by contradiction. We're supposing we have a subgroup of order 6. We see that it can't consist of elements of order at most 2 alone. It has to have at least 1 3 cycle. I'm going to look at what happens when it has 2 3 cycles. where tau is not sigma inverse, by the way. So you've got E sigma inverse, tau inverse so far. That's 5 elements. I'm going to see what happens with sigma tau. What is sigma tau equal to? Well, I'm going to have to make some assumptions. We're taking some arbitrary subgroup. It has 3 elements on this cycle. I might as well assume that those elements are 1, 2, and 3. I can go ahead and assume that they're in that order. If not, I can change the names of my variables or my symbols so that that's true. We'll let that be sigma. And what happens to tau? Well, note that tau has to have at least 2 elements in common with sigma. Up to how I choose to label my symbols, I can assume that it's 1 and 2. So either it's going to be 1, 2, 4, or it's going to be 1, 4, 2. So of course I can't force the 2 and the 1 to be consecutive. Well, what happens in the first case? 1, 2, 3, 1, 2, 4 becomes, well, 1 goes to 2, 2 goes to 3, 3 goes back to 1, 4 goes to 1, 1 goes to 2, 2 goes to 4. Oh, you get an element of order 2. What happens in this case? One goes to 4. And then that's it. 4 goes to 2, 2 goes to 3. 3 goes back to 1. Well, that didn't happen the way I wanted. Oh, I don't have to worry about it. If you're in this case, the inverse of this permutation is right there. So no matter what I see is that even if I have at least 2 3 cycles, I do get an element of order 2 in my group. So what I'm observing here is I must have an element of order 3 and some other element, say pi of order 2. Alright, so now I'm just assuming I have an element of order 3, a 3 cycle, and an element of order 2. I'm going to assume my 3 cycle looks like this. Let's suppose my element of order 2 looks like this one. If I do this product, I get this 3 cycle. And if I multiply by the inverse of this 3 cycle here, I get this 3 cycle. Note that since I'm closed under inversions, I need to have the inverses of these 2 elements as well. And now let's count 1 element, 2 element, 3 elements, 4 elements, 5 elements, 6 elements, 7. Oh, shoot. That's more than 6. So once you have at least 1 3 cycle and 1 2 cycle, you seem to have more than 6 elements. If there's any flaw in the argument right now, it's that I'm making an assumption that this is what my element of order 2 looks like. However, here's the other 2 cases. Suppose that this is my element of order 2. If I do the same calculations, again, I end up with distinct 3 cycles. And if you include their inverses, 2, 4, 5, 6, you end up with 7 non-trivial elements. Similarly with the remaining element of order 2. So these are 3 different cases of what H might look like, and in all 3 cases, H ends up having more than 6 elements. So once H has an element of order 3 and an element of order 2, it has at least 7 elements. And given that the size of H must divide 12, that means in each of these cases you actually have A4. Which is actually interesting, because coupled with our previous observations, that tells us that once you have at least two distinct 3 cycles that aren't inverses of each other, you end up in this situation. The smallest subgroup they generate is A4 as well. So all the subgroups of A4 are either a subgroup of a 3 cycle or a subgroup of that group consisting of the elements of order 2. One, 4, 2, 3. And that is it. Once you have two non-trivial 3 cycles, you end up getting all of A4, and once you have an element of order 2 and a 3 cycle, you get all of A4. In particular, there's nothing of order 6.